Hey, year 13s, it's good to see you guys. Thanks for coming. We are only missing Ben and Tenzi now. That's all we're missing. Hey, year 13s, it's good to see you guys. Yeah, it's a bit crackly on the sound, isn't it? It's a bit frustrating that. Tempted to unplug it and then plug it back. Hey guys, that'll be better. It always is whenever I get that issue. So just Ben missing now at this stage. Right guys, I'm going to crack straight on. Let's share screen. So today's lesson, before I move on to KP, I just want to spend a little bit of time. I might actually start KP in this lesson, depending on how we get on. So if I just switch, there we go. Don't want to switch to tablet mode. Heck no. Right, let's go on to this one. Right, so I've just grabbed a couple of questions. You guys will have noticed that I am slowly populating your support sheet, just to quickly give you a heads up. It's always nice for me just to make a point of this. So you guys really have been a driving force for me. In year 11, you guys drove me to be creating the support sheet for GCSE. And then, of course, you also then, when we went into A-level, you also drove me to creating the support sheet for the AS. And I am slowly putting together the support sheet for year 13. So this is what you guys now have access to. You can see all the ones I've populated. Now, the ones in this column, in column A, these are all notes. The notes are just from, I think they're from Save My Exams or from PMT. Can't remember exactly where they come from. If I click a link, it'll take you to one. The ones in white, you can't really find notes on. I may hyperlink in my notes that I make, but there's issues with that. I have populated all the booklets for Unit 4. Unit 4 is done, including super booklets. I actually have a second set in a super booklet. I'm happy to hyperlink that one in as well and add a column of super booklets too. I know that you guys tend to do loads and loads of questions. I'm busy working through Unit 5. I've started work on the benzene booklets. The super booklets are in because I've had them a while, but I will continue to populate this as we go along. I did the redox one because you guys had a test. I hope you found them useful. Okay, so today's lesson, we're just looking at, we've finished case C. Thanks for populating. You're very welcome, Ria. I haven't finished it just because it takes hours and hours and hours of me just trawling through papers trying to find questions, and I just haven't managed to have the time to get all of them done for Unit 5 yet. So for today's lesson, all I want to do is I just want to focus on having a look at some questions regarding KC. So I just grabbed a couple off the super booklets rather than the individual ones. I just grabbed a couple of these. So question number 1, an experiment was carried out to determine KC. Now, I need to make a point of this one. So you can actually add this. So this is, by the way, this lesson. Oh, Ben. All right, thanks, Ben. I'll mark you as in on the reg. Okay, guys, so I just need to make a real point of this particular question. And you can make some notes. This is just calculating KC. And it's a nota bene, really. Nota bene, common experiment, common KC EXP. Is esterification. So I'll give you an example. So let's keep it as simple as possible. Let's do ethanoic acid plus, let's go for methanol. Let's keep it as simple as possible. I could have gone for methanoic acid, but, and it's in equilibrium to form an ester, and water in this case. In fact, hang on a sec. They always form water, so an ester and water. Actually, that's not true because there are esterifications when we're in deriving carboxylic acid derivatives. You can actually substitute the carboxylic acid for 2 other families. We'll come to that later. But this equilibrium is a classic one that they tend to ask about. Now, the great thing is about these is these are all pure liquids. They're all liquids. So this is a homogeneous setup. However, the catalyst, and this is the nota bene really, the catalyst is a strong acid, usually hydrochloric in the questions to make it easier for you, amazingly. but the acid catalyst is HCl, and it's usually concentrated. It's actually, the note to make here is a few drops. A few drops, I'll actually put in the word a few drops of conch. Now, we usually actually use conch sulfuric. The problem is conch sulfuric adds in a level of complexity to the calculation. So I tend to see the questions appear with HCl. Now, you can use hydrochloric acid in the experiment. It's just H2SO4 is diprotic, which means you get twice as many H pluses, which means the catalyst is slightly more effective. But you can use HCl, and we would actually do this practically in class. We can't do, unfortunately, when we go back to school on Wednesday, we can't do any practicals until after the summer. So unfortunately, that's really sad news for me. That I really did fight for it, but unfortunately, we won't be doing any experiments. So I'm just going to quickly, there is that's actually what you'd name in an actual exam where they ask you for the catalyst for esterification. But the one that tends to be used for KC is this one. Yeah, used for KC. And there is a reason, and you'll see this in a second. So in this question, the great thing about this question is it's lovely and short. So I'm actually going to do an odd thing. I'm just going to quickly snip the question. And you can see it's worth 6 marks. So I'm actually going to produce a second copy of this within these particular notes. Oh, well, let's see if that keeps it. Let's see what that does. Paste. There we go. Right, so I just want to show you how this question pans out. So it says 0.10 moles of ethanoic acid was added to 0.20220 moles of ethanol. Now, I just want to make another note to Bene. That's very uncommon. Yeah, just to quickly mention these, they've been nice in this question. Yeah, the nice thing is that they've given us moles straight off the bat. A lot of the time, what they will actually do, and again, it's a nota bene for the experiments. Yeah, the liquids, let's try that again. The liquids are measured in centimeters cubed, which makes total sense. Yeah, if you've got a fluid and you're gonna mix together a mixture, you're going to be using a measuring cylinder. You're not going to do anything else. So the liquids are measured in centimeters cubed, but you are given their densities. Oops. You're given their densities. Now, what this means is, so in EG, they would say measure out 4 centimeters cubed, and they're going to give you, and let's say of ethanol, 4 centimeters cubed of ethanol liquid. Yeah, and it's going to give you the density as 0.79 grams per centimeter cubed. So they're going to give, now what that means is, if you can actually now calculate grams from this. We realize that for KC requires moles. Yeah, requires moles, and then usually requires you to translate that into concentration as well. Yeah, but in this case, because the equations are one-to-one, but what you would then do is you would multiply the volume by the density, and what that will give you is it's going to give you the grams by the density, which will give you the grams that you added to the mixture, and then you can do grams over rams. Yeah, 4 times 0.79 gives me 3.16 grams. And then you can divide it by 46.0, the MR of ethanol. Yeah, and you can work out moles. So divided by 46 gives me a moles in this scenario of 0.69, 3 sig fig. 687 is the numbers moles. And you can just see that it's already given it to us. Yeah, they've already given it to us. We could actually work out the volumes of these by reversing those equations, but it's just for me to give you a nota bene that there is awfully common. Watch out for densities. If they give you a density and a volume, just multiply them together. Right, it says calculate KC. Now, the first thing you always do with KC is you want to build a roadmap. So we have got ethanoic acid, and this is how I would, if I was going to do this in an exam, this is how I would go about doing this. Yeah, they're probably going to have given you they're probably going to have given you the equation already, probably. Yeah, But what I also now do is I then translate immediately to Kc. Now, Kc, of course, is products over reactants. So we've got ester. I'm going to be good and actually do the entire thing today. It's not like me. Yeah. Times by the concentration of water. Yeah. All over the ethanoic acid. Ethanoic acid multiplied by the ethanol. There we go. So I'm just, what this is a roadmap for my calculation. So what I need to know is moles of everyone at equilibrium. So what it said is, it said 0.12 moles of ethanoic acid was added to ethanol. So I'm now writing down the word initial. Yeah, ini. And I've put in 0.120 moles of that. They've been very nice to us. And 0.220 moles of that guy. I've got 0 of that. Now, here's the clever bit. The hydrochloric acid is 1 molar. What that means is it's dilute, which means I can also treat the water, since HCl is a gas, I can also say that the water I've got in the addition to this mixture, yeah, I've actually got 5 centimeters cubed of water as well, which comes from the catalyst. This is why I wanted to spend the time looking at these questions, because there's a level of complexity here in the calculation that just requires you to take a bit of time over it. Now, 5 centimeters cubed, of course, translates to 5 grams of water. We haven't got moles yet, so we can now work out the moles of water, grams over rams. Water weighs 18.0, 5 divided by 18, and I've already got in the starting mixture, I'm just going to quickly flag this up here, 5 centimeters cubed, which translate to 5 grams because the density is 1 gram per centimeter cubed, divided by 18.0, and I get a number of moles of 0.278 for the moles of water at the start, and 0 moles of ester. Right, what I'm now going to do is I'm just going to move this down a bit, give me a bit more space. There we go. And now I'm going to write down equi, because what I need is I now need equimole. I need the equilibrium moles to be able to calculate Kc. It says that the mixture was then left to reach equilibrium, and it says the mixture was titrated with sodium hydroxide, which reacts with both acids, the mean titer. Right, so we now realize that there's a second reaction going on. Yeah, we realize that we can now calculate the moles of sodium hydroxide. So they're doing something clever here. How do you actually work out the position of an equilibrium? You need someone who you can detect, and we can detect acids by titration. You've got to titrate it quick, because otherwise the equilibrium is going to respond. Yeah, so you titrate it all in one go and rapidly. So it's a difficult practical. Being able to get a reasonable value for this is very challenging for students. So you can still titrate samples, by the way. You can still do that. You just have to be really fast with them. It's really tricky. Right. The entire, now the question, this is the mixture was titrated. They haven't bothered taking a sample. They're just titrating the whole thing. And they've given us sodium hydroxide. So this is where our calculation actually starts. Now, our sodium hydroxide is going to react with both ethanoic acid, the leftover ethanoic acid at equilibrium, yeah, to form sodium ethanoate, yeah, and water. But it's also going to react with the hydrochloric acid catalyst. That's one of the nightmares. Now, remember, the catalyst doesn't change. Yeah, the catalyst doesn't change because it's never used up. So it's actually going to do both of these. So what we now need to do is we now need to work out sodium hydroxide moles in total. Yeah, so if we just do sodium hydroxide moles total, we had a concentration of 1 molar, 1 mole per dm cubed. No, can't do that. It's GCSE. Sorry about that. 1 mole per dm cubed, and the total volume used was 45 centimeters cubed. Right, we can now use number of moles equals C times V over 1,000. Yeah, so we can do concentration is 1 times by 45 all over 1,000, which is going to give me 4.5 times 10 to the minus 2, I believe. Times 10 to the minus 2. Let's just quickly check that. 45 divided by 1,000 gives me 4.5 times 10 to the minus 2. I like it. Or, as my calculator has decided to spit out, 45 times 10 to the minus 3. I don't really care how you represent it as long as it's correct. Right, so this is the total moles of sodium hydroxide. Now what we need to do is we need to work out the moles of catalyst. So the moles of catalyst was 5 centimeters cubed in 1 molar. So we now go HCl catalyst, HCl cat. So it was 1 mole per dm cubed, and it was 5 centimeters cubed. Yeah, so then we can go number of moles is C times V. C times by V over 1,000. Yeah, so 5 divided by 1,000 gives me 5 exponential minus 3. Of course it does, 5 exponential minus 3. Right, now remember that's 45 times 10 to the minus 3. Yeah, if you want to, you can actually do it the other way. You can go 4.5 times 10 to the minus 2 if you prefer. It makes no difference to me. As long as you get the numbers right in your calculation, doesn't matter. Right, now what's going to happen is, so we now know that 5 times 10 to the minus 3 moles of sodium hydroxide is going to be used to calculate, it's going to be used to neutralize the hydrochloric acid catalyst. So what that means is we now need to do sodium hydroxide that reacted with the equilibrium ethanoic. Yeah, and what you need to do is we need to take the sodium hydroxide, 4.5 times 10 to the minus 2, and we need to minus the catalyst moles. Now we can do this because it's a one-to-one relationship. Yeah, both of these reactions, this is why they don't want to use the sulfuric. It adds an extra level of complexity. These are all one-to-one-to-one-to-ones. So the moles of hydrochloric acid is equal to the moles of sodium hydroxide that react with it, so we can just minus it away. So 4.5 exponential minus 2 minus answer, 5 exponential, gives me 0.04 moles of sodium hydroxide that reacted with the ethanoic acid. Yeah, I'll do reacted. I'll actually be good. I'll note everything. Reacted with the ethanoic. Now, once again, it's a one-to-one relationship. What that means is I've just worked out my equilibrium moles. Yeah, that then translates to 0.04 moles of ethanoic acid at equilibrium. You realize why this is complicated and why I'm wanting to spend a bit of time to go through it. So what that now means is I've now got my number. I've got, oh, hang on a sec. Oh, yeah, 0.04. That makes total sense. If it was bigger, I'd be worried. 0.04 moles of that at equilibrium. Right, we can now work out the change X. Yeah, change X is going to be the bigger minus the smaller. It's 0.102 minus 0.04. Yeah, 0.1, which is 0.08, isn't it? Minus 0.04. So X is equal to 0.08. Right, so this one's going to go down by, this is going to be 0.20 minus 0.08. This one's going to be 0 plus 0.08. And this one's going to be 0.278 plus 0.08. So we can do the maths now and work out each individual one. 0.220 minus 0.08, which gives me a moles number, which I will then highlight. Yeah, I'm now going to just quickly flag up as the one I need this one, and I need this one. Yeah, and then I can work out the others. This one's easy. This one's just 0.08. That's the one I need for my Kc value. And this one, of course, is 0.278 plus 0.08. And the water bit is a real tricky bit there, 538, and there's my moles of water at equilibrium. Right, now I don't have to convert to concentration here because it's a one-to-one-to-one in the equilibrium equation, which means I can insert moles directly. I can now create the final Kc. Want to go Kc equals Ka. Kc equals products 0.08 multiplied by the power of 1, because it's a 1 in the stoichiometric ratio, multiplied by water at 0.358, all over ethanoic at 0.04. How does the minusing give the moles reacted with ethanoic acid? So the reason why it does that, Ivan, is because the sodium hydroxide was reacting to, in these two, I gave you both equations. Those are the two things that are reacting with it. We just worked out that there was a total for sodium hydroxide of, sodium hydroxide was, so we had a total of these two of 4.5 times 10 to the minus 2. And we realized that some of it's reacting with the HCl and some of it's reacting with the ethanoic. Well, if we can work out the moles of hydrochloric, which was 5 times 10 to the minus 3, we realized that the moles of sodium hydroxide was 5 times 10 to the minus 3 that reacted with it. Therefore, I can minus it from this guy to work out the amount that reacted with that. Does that make sense, Ivan? Give me a shout out on the chat if that's okay, if you understand that now. It's why I gave you both equations so you can see it. Yeah, okay. So now I'm just inputting my data into Kc, to be fair. Yeah, and the ethanol, okay, thank you. No problem at all. So the ethanol is then going to be brackets, I'll put the bracket there, 0.14 moles. As I said, I haven't needed the nota bene. I can use moles. I can use moles directly. Yeah, you always know when you can't because they give you a volume. I can use moles directly since equation is all the same. Since equation is a 1 to 1 to 1 to 1. Yeah, if it was a 2 to 2 to 2, then it would be the same thing. Yeah, you can only do it in that scenario. Otherwise, you need a volume. Right, I can now run that through my KC value. 0.05 multiplied by 0.358. So that gives me a top number of 0.02864 all over 0.04 multiplied by 0.14. And that's going to give me 5 times 10 to the minus 3. 5.6 times 10 to the minus 3. 5.6 times 10 to the minus 3. Divide the top number by the bottom number, 0.02864 divided by 5.6 exponential minus 3. And I get 0.02864 divided by 5.6 exponential minus 3. And that gives me a KC value of 5.11. And there are no units for KC since moles per dm cubed cancels, no units. No units. We're done. So that's meant to be done in 6 minutes, folks. That's what I need you guys to recognize, that that's what you're dealing with. Yeah, I know it's hard. That's challenging. It requires an awful lot of chemistry. You get quicker as you do it. Let's look at the next question and see whether it's easier or harder. Yeah, right. Next question. Nitrogen. Now, look what they've done now. That's interesting. This one was just a flat 6 marks. Yeah, but this one's now broken it up for you. It shows how variable they can be. Yeah, so it says nitrogen dioxide dissociates according to the following equation. Right, guys, notice 2 on this side, 3 on this side. Can't use moles, have to use concentration. And look, they've given us a vol. Yeah, that's because the equation's not a 1-to-1-to-1. Right, when 21.3 grams of nitrogen dioxide was heated to a constant temperature T in a flask of volume 11.5, an equilibrium mixture was formed which contained 7.04 grams of oxygen. Calculate the number of moles of oxygen present in equilibrium and the mole of nitrogen monoxide at the present of this equilibrium. Right, okay. So what we're doing is I'm going to zoom right in and go ini. I'm going to put ini on top and equi underneath. Yeah, I think that seems like a reasonable idea. Yeah, well, the great thing is, of course, this means 0 and 0 with that because it's mentioned 21.3 grams. 21.3 grams. We can't work in grams within an equation. We've got to work in moles. Yeah. Now, the great thing is it also gave me at equilibrium 7.04 grams of oxygen. Now, the fab thing is we don't really need to worry about the moles at the beginning because it's already given us X in the change from 0. So what that means is all I need to do is convert to moles, and we all know that oxygen weighs 32.0. So 7.04 divided by 32.0 will give me a moles at equilibrium of 0.22. Now that's 1x because we've got a 1 in front of it. This is a 2x, so I need to double that to give me 0.44 moles of that at equilibrium. Now the great thing is this is going to go down by minus 2x. This is minus 2x. Yeah, so I'm going to say, I can't work out the moles of that because I haven't worked out the moles of original. That's going to be a problem, isn't it? They're going to vast it down here. So the moles of oxygen at equilibrium is going to be 7.04 grams divided by 32.0, and I get a 0.22 moles at equilibrium. We know that that's in a 2-to-1 ratio with nitrogen monoxide, so the moles of equilibrium for that one is going to be 0.44. Next, right, calculate the number of moles in the original, and hence calculate the number of moles present in the equilibrium mixture. Right, so we've got to work out nitrogen, of course, NO, yeah, work out its MR, because it's grams over rams. So nitrogen is 14.0 plus oxygen at 16.0, which gives us 30. It's nice and easy. So we've got the number of moles original is 21.3. 21.3 divided by 30.0, yeah, 21.3 divided by 30.0 gives me moles at equilibrium of 0.71 moles at no, that's initial. Moles at equilibrium, it's going to drop by 2x, which was the same as the 0.44. So minus 0.44. My moles at equilibrium is 0.71 minus 0.44, which was 2x. Yes, my moles at equilibrium is 0.27. moles at equilibrium. Right, next, write an expression for Kc and hence calculate its value. Right, so Kc equals products over reactants. So I'm assuming that's NO. Oh, have I made a mistake? I've made a mistake, folks. Sorry, no one caught me. It's NO2. That's where my 2x is causing me troubles. Yeah, so sorry, I need to times that by 2. Apologies, I've made a mistake. Yeah, I've made a mistake. Isn't it 46? Yes, thank you, Dana. She caught it as well. 46.0. Yeah. So that's the same as ethanol as well, 21.3 divided by 46. Thank you, Donna. Well done for catching it. 0.463. There we go. Right. So then we have moles 0.463 minus 0.44. Yeah, 0.463 minus 0.44 gives me 0.023 moles. Then I can create my Kc expression, NO2 to the power of 2, I believe, for that guy. Yeah, all over NO2 to the power of 2, stoichiometric ratio. Right, now, of course, now the trap to this is that students have a really bad habit of inserting these numbers now directly into the equation, and you can't. Because this is an unequal equation, you've got to take account for the 11.5. Yeah, so what I'm going to do is I'm just going to go conc. Yeah, number of moles divided by the volume will give me concentration. Yeah, so I can do NO concentration. So the NO at equilibrium, which was up there, was 0. So we have NO is 0.44 moles. Yeah, divide that. So 0.44 divided by 11.5. Yeah, divide that by 11.5. Yeah, and I get a concentration of 0.0383 in square brackets. Right, and that's to the power of 2. Then we go oxygen concentration. Oxygen concentration is moles is 0.22. 0.22 divided by 11.5, same volume. Yeah, 0.22 divided by 11.5. And I get a concentration of 0.0191 square brackets to the power of 1. And then NO2, which I've just calculated at equilibrium, yeah, which is going to be 0. This is why I write it underneath like the other one, 0.023 divided by 11.5. 0.023 divided by 11.5 gives me 2 times 10 to the minus 3. Right, now I can put these into my Kc value, into my Kc expression. Yeah, so Kc equals, by the way, there's more space in the actual question. So the the NO, yeah, is 0.0383 to the power of 2, multiplied by 0.0191 to the power of 1, all over 2 times 10 to the minus 3, 2 times 10 to the minus 3, multiplied to the power of 2. So do the top one first, 0.0383 squared multiplied by 0.0191. So that now converts to 2.80 times 10 to the minus 5. Yeah, all over, divide that by brackets, 2 exponential minus 3 squared. Yeah, and I get, 7. Kc equals 7.00. Units, it does have units. Those two cancel. It's moles per dm cubed. Nice. So it's just nice to show you guys what's expected of you from Kc, because it's so easy to get stuck in a routine of thinking you know what you're doing and then to be absolutely battered when you hit a question. Yeah, so do just bear that in mind. Yeah. If I go to the next one. Okay, so when heated to 100 degrees C, nitrosyl chloride partially dissociates, decomposes to form nitrogen oxide and chlorine. Calculate the moles of chlorine at the equilibrium mixture. What's a big Kc value and what's a small Kc value? Is that dumb? No, Dana, it's not a dumb question at all. Annoyingly, like Kc can be any value. You can have enormous Kcs and very small Kcs. Small Kcs are anything in 10 to the power of like, I don't know, -2 and up and down. Yeah, and then big Kc is 100 plus. Anything in triple figures is, well, I mean, anything above 0 is big. So it's not a dumb question at all. What you're doing is you're asking so that you can add it as a flag. So if you get a stupid number, it's really tricky with KC. You don't really have any rhyme nor reason to the particular size of them. They're very reasonable numbers. I will have rounding errors all over the place for this guy, which is a nightmare. But they give you a range, so that takes into account the rounding errors. I could check the mark scheme, but I can't remember which booklets I pinched it from. You can have a try and see if I can find it. Oh, I might be able to find it in this one, at least one of them on this one. See how long it takes me to track down this question, and then we can track down the mark scheme. Just check, because I'm always, question number 1. Lol. Is there another one on this booklet? I bet there isn't. It's not going to have what I want. No, it's not. I'll do the next question and we can check our answer across that one. It might be in set number 1. Equal. These are my super booklets, by the way. Exam questions. Let's see if I can find this one. Don't know where exactly they'll be. I mean, I probably should recognize it now that I've just calculated it. Oh, it's not there either. It's not a very long super booklet, is it? That's a bit frustrating. Don't know where it's come from. It will have come from another booklet that I've got somewhere. Not that it matters. Mr. Duncan, after class, could you please send the message and the answers to the moles on equilibrium homework? Yes, of course I can, Emma. It's absolutely no problem at all. I did recognize that I hadn't. I just really wanted to get through and show you guys really what the exam questions really look like. That's all. Right, I'm gonna do a couple more. I wanted to focus on KC today rather than moving on to KP. So let's run this one. This one might be easier. Yeah, no problem at all, Emma. Okay, 2.5 mole sample was heated. It's told us initial. So let's put ini above and equi below. So the initial was 2.50 moles, and it's actually given us mole. That's nice. And 0 and 0. Yeah, I'll actually just put over here mole. It's nice of them. It's heated, and the equilibrium mixture contains 0.8 of NO. So NO here is a 2 in front of it, which means that's 2x, which means the chlorine went up by half of that, and the NOCL went down by the same number as that. So 2.5 minus 0.8 gives me 1.7, and these are in moles as well, which is nice. I need concentration because the equation is not a 1-to-1 to 1-to-1. Yeah, so we can calculate those moles. The chlorine is 0.4 moles, and the NOCL is 1.7 moles. Not complicated. Nice and easy that. Nice and easy start that, because they gave me moles, so I don't have to work too hard on it. A different mixture of NOCL reached equilibrium in a sealed container of 15. They've given us a volume. That's because the equation's not equal on either sides. The equilibrium mixture forms this, and this, a temperature. Calculate the value of Kc at this. Oh, they've given us the Kc value. Oh, interesting. They're gonna have to make us. They're gonna make us reorganize. Write the expression. Kc equals products. So NO to the power of 2, Cl2 to the power of 1, all over NOCL to the power of 2. There's Kc, nice and easy. Right, calculate the moles of chlorine in the equal. Right, so we need to reorganize. So we've got to do the divide first. So Kc multiplied by NOCL to the power of 2, divided by NO to the power of 2. Yeah, it's going to give me Cl concentration. They've asked me for moles. It's a clever game, this. Yeah, that's going to equal Cl2 concentration. Let's run through my numbers since I have been given them all. Yeah, Kc is 7.4 times 10 to the minus 3, multiplied by NOCL. There you go, 1.9 squared, all over 0.86 squared. 7.4 exponential minus 3, multiplied by 1.9 to the squared. Divide that by 0.86 squared, and I get a chlorine concentration of 0.0361 moles per dm cubed. Now, the problem is they haven't asked me for that. They've asked me for moles. So the great thing is, what was my volume? 15. Yeah? I had 15, so number of moles equals C times by V over 1,000. Well, I've got concentration and I've got the volume. So input my numbers, 0.0361, which is on my calculator, times by a volume of 15. I don't need the 1,000 because I'm in dm cubed since it's a gas. It's very interesting. So multiply that by 15. I'm going to get no rounding errors at all now. And I end up with 0.542 moles of chlorine at equilibrium. Next, consider the alternative equation. They've halved it. Right, so if you halve the equation, you're going to square root the Kc value. Yeah, I know that seems mad. I'm sorry that I can do that. I can run the long way if you like. Yeah, you can actually literally just take the Kc value, which was, Kc was 7.4 times 10 to the minus 3, root it, and it'll give me 7.4 exponential minus 3, root answer, and I get a Kc value of 0.0860. And the units are going to be, that cancels with that, so it's going to be giving me a half on the bottom. No, half on the top. We had products over reactants, moles per dm cubed for the NO, and then we had Cl at the power of a half, which gives me moles to the half, dm to the minus 1.5. Yeah, and then that cancels out with the moles per dm cubed of the other guy, of Nockel. Yeah, so that cancels with that. So my units are moles to the half, dm to the minus 1.5, because I'm already on top, so I don't have to take the reciprocal. Clever game. Do you want me to? I can run that through for you if you like, guys, all the way through. Like, some students don't like these tricks. You can simply insert the numbers to their powers and it'll give you the same number. Just to show you that, yeah, if I put these in still with their same numbers, yeah, so I've got the concentration. There's the concentration of chlorine. Yeah, here's the concentration. Try and track down everything. Yeah. Oh, I made a mistake. I made a mistake, folks. It's come out in the wash. It's come out in the wash because I've done the classic mistake, haven't I? Guys, I've made an error. Nobody caught it. Neither did I. Oh dear. Right. So I stuffed that up. Ignore all of that. That's hilarious. It's all wrong. It's all wrong. It's because I'm writing in big. It's totally, that's what I'm blaming it on. I needed to work out the concentration and I didn't do it. I had to take into account the 15. I totally flummoxed that. God, that'd be a lot of time in the exam wasted. Nockel is moles. Yeah, so I need to first of all do is Nockel is 1.9 divided by, moles divided by volume gives me moles per dm cubed, divided by 15. It made totally flummoxed that one. Divided by 15 gives me 0.127 moles per dm cubed. There you go. There's my number. So the Kc, and that's Nockel. Yeah. So this becomes multiplied by 0.127 squared. Yeah. All over NO. They told me NO moles as well. So NO moles is 0.86 divided by 15, the volume. 0.86 divided by 15. Totally flummoxed it. Flummoxed. Haven't used that word in a while. There we go. Now I can insert that one. And it is squared still. 7.3 squared. Yeah, so 7.4 exponential minus 3 multiplied by 0.127 squared. Yeah, divided by 0.0573 squared equals, my Kc value is 0.0364. There we go. And the units, probably we're going to have its units, aren't we? Cancel. Oh, hang on a minute. That was working out the moles. That's right. Sorry. That's not Kc. I used Kc. Yeah, that's chlorine concentration. Chlorine conc. Now I need to multiply that by 15 times by 15. The moles of chlorine was 0.545 moles of chlorine at equilibrium. There's my final answer. What a nightmare. Ruined that. Now I can input them down here if I want to. I would have got, the Kc I would have still got right. Lol. Wow, that was really tough. Let's check the mark scheme because I actually do know where that one came from. It was the very first question on that first booklet, A2 Chem, book set 2. I think it was set 2, wasn't it? Equilibrium. I totally flummoxed that one, guys. If I was in an exam, I'd be really now pushing for time. You really don't want to make those mistakes. That's why you need to be well practiced. Right, there's the question. So let's go to the mark scheme. And it's question number 1 on the mark scheme. There it is. A, chlorine. Have I made a mistake? Oh, no. There we go, 0.54. Spot on, right in the middle of where I wanted. Yeah, so easily done. So easily done, root answer, 0.86. There you go. So I wanted to spend a bit of time here, guys, doing these so you could see just how hard these are. These are really challenging. They're just calculations that requires you to have a bit of thought. And if you get that wrong in an exam, you're going to drink your time. Yeah, that actually brings me to the end of my lesson. I'll post the answers. In fact, I'll quickly run through them if you like. Don't think it's going to take me very long to do it. So I just wanted to show you what real KC looks like, guys. Just going to do that and insert printout. Now, I think I gave you, did I give you moles 1 and 2, Emma? Documents, year 13. Oh, no, kinetics. Where's the equilibrium homeworks? Ooh, documents, backup, pen drive, backup, teaching file. How come you just square rooted the CL2? I didn't square root the CL2. I square rooted the KC value. That's what I square rooted, Ivan. I'll go back to it in a sec. Teaching file. I don't know where anything is now. This is a nightmare. A level, resources, A2, unit 4, equilibria. It's not there. Oh, they're here. So let's insert that one. Right. I like it. Okay. Super quick, guys. So this is out of 15. I've got 11 minutes left of this lesson. Let's see how long it takes me to do it. 1x, 1.2, decrease by 1x, 0.6, 0.6. I'm done. Initial, equi, difference, 0.03. I need a calculator just so I can stuff it up. Yeah. So that's 0.03 there, gives me the x check 0.03. That's going to decrease by 3 times that. 0.1 minus 0.03 times 3. What? What? Oh, 0.1 minus 0.03 times 3 gives me 0.1. Oh, stupid calculator. 0.1 minus 0.03 times 3. Right, 0.01. Right, this one's going to go up by twice that to become 0.06. Tick it if you've got it. Tick, tick. Next one, decrease by 7, increase by twice 7. Tick it if you got it. Next one, increase by that. Oh, 3 times is going to 0.4 minus that, and that one then drops by 0.8. Tick it if you've got it, folks. Next, that's 2x. So that's going to drop by the same amount. So that's going to drop to 1.3. And this one's going to drop by half that number. 2 minus 0.35 gives me 1.65. Tick it if you've got it. Next one. This one, oh, initial moles. That's interesting. It's gone up by the same amount. And that's going to decrease by the same amount to 0.2. Tick it if you've got it. Next, this one's gone up by 0.6, so x is 0.2, because, oh, hang on a sec, that's tricky. Hang on, 0.4 divided by 3. That's tricky. That's 2x, that's 3x, isn't it? Gained 3x. And it's gone up by 0.6, divided by 3 gives me 0.2. Okay, so there's x. Yeah, that one's going to go up by it, so that one's going to end up at 1.2. This one's going to go down by it, because it's a 1-to-1-to-1 now. 0.8 and 0.8. Tick it if you've got it. Yeah, next. Next, that one. Ooh, how fascinating. 0.01. Have I made a mistake? Have I made a mistake? What question have I made a mistake on? What question have I made a mistake on? Where? No. Nope. Okay. Okay. I'll keep going. You were taking too long. That's hilarious. The equilibrium's gone back in that direction. How fascinating is that? That's gone down by 2x. So that's minus 2x. So that's 1 equals 2x. So 0.5 is x. So that's going to gain x at 3x. So that's going to go up to 1.5. That's going to go up, and that's going to go up by 1x. So that's going to go up to 10.5. Tick them if you've got them. Next, that one's gone down by 2x. That one's going to go down by, that's 2x. That's gone down by 1x. 0.4, so 0.2, 0.3. This one's going to go up by 1x, 0.2. Tick them if you've got them. Next, this one's also going to go up by 0.4, and this one's going to go down by 0.4, 1 to 1 to 1. That's nice and easy. Yeah, this one's gone down by 0.2. This one's going to go up by 0.2. This one's going to go down by 0.4, which brings me to 0.8. Tick them if you've got them. Next one, that there is going to be 0.3 is x. So that's going to drop by 3 times that and take me to 0.1. That's going to go up by that value at 0.3, and that one's going to go up by that value 0.3. Tick them if you've got them. Next, this one's going to go up by 1 point. That's going to go to 1.5. This one's going to drop by that number, so 9.5. And this one's going to drop by twice that, so 4.0. Tick it if you've got it. Next, this one's going to drop by 3x. Yeah, and that 3x is 0.6, so x is 0.2. This one's going to go up by 2 of those. This one's going to go up by 1 of those. And this one's going to go down by 1 of them, so 1.8. Tick them if you got them. Next one, this has gone up by 2x. This one's going to go minus. This is going to be 2 minus. Yeah, 2 minus 3x. And this is going to be 2 minus x. And we're done. Tick them if you got them. Amazing. Yeah, I like it. Clever game. So out of 15 for quantities 1. Let's see if I can do the other one. 6 minutes to go. 6 minutes to go. I feel like number 2 is going to be harder. Let's have a look, though. Let's see if I can get them done in that time. Record-breaking chemistry lesson. Right. Okay, so I believe this one's different. Oh, yes. So that one's dropped by 0.2. This one's going to drop by 3 times that value, so 0.6. That becomes 0.4. This one's going to go up by twice that of 0.4 as well. Isn't that clever? Yeah, next one, this one's dropped by 0.9, and divide that by 3 to get 1x gives you 0.3. This is going to increase by twice that. This is one going to decrease by 1 times that. Tick them if you've got them. It's clever, isn't it? Tick it. Next, this one's dropped by 1.4. This one's going to drop by the same 1.4. This one's going to go up by twice 1.4, which is 2.8. Tick him if you've got him. 15. Is that 15 out of 15, or have I made a mistake somewhere? Did I make a mistake? This one's gone up. This one's gone up by 0.4, but that's 2x. So x is 0.2. Nope. Okay, good. X is 0.2. This is going to decrease by that. So that's going to end up at 4.8. And this is going to end up at 0.8. Tick it if you got them. Next, this one's gone down by 0.6, which is 2x. So x is 0.3. This one's going to go down by that value. So tick it. This one's going to be up by twice that, 0.6. Tick them if you got them. Next thing, this one's gone up. Oh, interesting. Equilibrium's gone in that direction. How fascinating. So that one's gone up by 2x. So x is 1.5. This one's going to go up by 0.15. And this one's going to go down by 0.3. So that drops to 0.7. Tick them if you've got them. Next, that one's gone up by 0.4. It's 1x. That one's going to go up by 0.4 as well. This one's going to go down by 0.4. Tick them if you got them. Next, This one's gone up by 0.3. That's 1x. This one's also going to go up by 0.3. And this one's going to go down by the same number, 1.7. Tick them if you got them. Next ones, we're nearly there. 3 minutes to go. This is going to be tight. It's going to be tight. Next, this one's gone down by 3x. Yeah, if that one's gone down by 3x. 4 minus 2.5 gives me 1.5 divided by 3. X is 0.5. Yeah, this one's going to go down by 1x, so that's going to drop to 1.5. This one's going to go up by 0.5. This one's going to go up by 0.5. Tick them if you got them. Next, 1 minus x. This one's going to go down by 3 minus 3x. And this one's going to be 0 plus 2x. Tick it if you got it. This one's going to be 2. That's up by 2x. This one's going to go 2 minus 1x. And this one's going to be 2 minus 3x. Tick it if you got it. Next, this one's gone down by x. This one's going to go 0 plus 2x. They will just accept 2x there if you like. Yeah, totally acceptable. This is now the same thing. So that's 3 minus x, the same numbers. Tick them if you got them. Next, that's 1 minus x. This is going to be 2x. And this is going to be 1 minus 2x. Next, this is x. That's interesting. That's going to be 1 plus x. And this is going to be 2 minus x. Last question. I'm nearly there with 2 minutes to go. 1 minus 2x. This is going to be 2 minus 1x. And this one's going to be 1 plus 2x. And I'm done. Tick, 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 tick. Woo! Wow, that's how quick you can do those homeworks. Under 10 minutes, 2 homework sheets. How'd you get on, folks? So this sheet, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Total is out of 30. Let's add it to the spreadsheet. Let's just do it as a singular homework, folks. Yeah, so let's go to Google. I'm sorry if you have another lesson in 1 minute. If you have a chance, please add them to your homework tracking sheet. If I can find it. Where's my homework tracking sheet? Don't know. It's gone. Where's it gone? I don't know where it's gone. A2 homeworks. Well, that's bum. I seem to have lost it. Was that it? A2 homework tracking sheet. When was the last time we used it? What the devil? A2 homework tracking sheet. It's gone. Where's my A2 homework? I found it. Found it. Found it, found it, found it. Let's get rid of that. I've just totally lost it. I found it and then closed it. Guys, if you need to go for your next lesson, please do. Yeah, just leave. Otherwise, you can insert your numbers into my tracking sheet, which I'm hoping is going to come up. No. Really struggling with this. Thank you. No worries. You go. We all have Ken with Miss Childs. Yeah, go, 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 folks. You go. You insert your numbers. I'll get rid of it. Guys, I'll leave you be. Thanks for coming. I'm sorry it was a full lesson. I'll see you guys all next lesson. And in fact, I'll see you for real. See you later, guys. Ciao.